Well, thank you for the introduction. My name is Weiheng Zhong, and I'm a second year PhD student in Uncertain Conviction Group instructed by Professor Harding Madani. And today, it's my honor to be here to present our recent research progress, which is explainable machine learning for learning the spatial-temporal pattern of the dynamic system. So it is also part of the joint project with Argonne National Lab with my collaborator Tammy Mali under the supervision of Professor Prasanna Balapakash. So this is the pointer. Yeah. So let me first go through the presentation outline. First, I will show some motivation of our research, and then I will present some background information and our proposed solution. The results of a case study is also shown, and finally comes to the conclusion to give some takeaway message. So motivation. First is traffic prediction is a very important component in traffic intelligent traffic system. Using traffic prediction, we can inform of the potential traffic congestions or the potential traffic accidents, so that we can do something in advance to prevent this happening. And traffic prediction is also important for many real-world applications by taking the predicted traffic condition into consideration. Many applications such as traffic signal control or navigation system can achieve better performance for the users. But as many research points out, the congestions now will last more than 3 hours every weekday, morning and evening. It is also observed in the highway system of the Bay Area. Here, this is the part of the highway system in California, and we show that in many locations, the traffic congestion duration is over 4 hours per day. However, most short-term prediction models typically they are taking care of 1 hour ahead prediction. And it is not enough to deal with this congestion prediction. And on the other hand, we test this model to predict further future traffic, which the result is shown on the right, which show that as we increase the prediction horizon from 1 hour to 6 hours, the error will accumulate dramatically. Hence, we are looking forward for a more advanced model that can take care of the long-term traffic prediction. The other thing that we are concerned about is that most traffic prediction models are black box models. What it means is that we know the model can perform very good, but we don't know how exactly it works. So this will, as you can see in the figure on the left, deep learning model will have a relatively high accuracy but lack of explainability. Of course, we can use some more explainable deep learning models to predict the traffic future. However, usually the accuracy will drop. And traffic management becomes a more decision-sensitive area. Many research points out that the congestion cost of US is growing and growing. In some big cities such as New York, the annual traffic congestion cost can over $11 billion. On the other hand, many new rising applications such as autonomous vehicle, where a bad decision or wrong decision will lead to a very critical consequence. Under these conditions, we consider that traffic management become a sensitivity area, which needs our prediction model and our management model to be trustworthy and reliable. So summing up the previous two slides, basically we are trying to deal with two challenges. First is how to increase our prediction horizon. Second is how to explain our prediction. And our proposed solution is attention-based graph neural network. Before I introduce my method, let me go through some background information. First, I want to introduce this graph neural network, and I will start with some more broad concepts such as machine learning and deep learning. So what is machine learning? Machine learning basically refers to the algorithm that imitate the way that human learns new knowledge. In the cases of teaching a machine to classify a dog and a cat. So we are basically like treating the machine a 3-year-old kid, right? We give them a picture and tell the machine that it is a dog. We give the pictures of a cat, and then we tell the machine that it is a cat. we use large amounts of this picture to go through this process until the machine can achieve satisfactory performance. But how to design the machines remain open questions. So deep learning basically is one type of way to design the machine. So it is the machine learning models that use deep neural network, which is inspired from the biological neural network of human brain. So in the deep learning model, we have multiple hidden layers, which is shown here. And in each hidden layer, we will have many neurons. Each neuron will take care of a small part of the computation. But when all these neurons work together, the model can take care of a very complex computation. So which is very similar to a biological neural network in human brain. And for each neuron, you have infinity choice to design it with a changeable parameter. And during the training, the model will adjust the parameter to achieve a higher performance. And to provide more details, it's like we will calculate the loss function by comparing the output and the ground truth. So if the output is close to the ground truth, typically we have a smaller loss function, which means your model is performing better. And how to adjust the parameter is using stochastic gradient descent, which is shown in the lower figure. Because I think we all are familiar with gradient descent, so I will skip this part. So now let's come to the graph neural network. Graph neural network, also called as graph convolution neural network. So let's start with the convolution neural network. It actually simulates how people look at the picture by aggregating the features pixel by in the range of all the pixels. And graph neural network implement how people understand the network system. So as you can see here, we will aggregate a feature not only based on the distance, but also based on the connectivity of the graph. So for example, for the yellow node, only the node connected to the yellow node can pass the message to that and can aggregate the message to update the node embedded, which is very similar to the traffic system dynamic in the real world, that the congested node will affect the location which are not congested. And the other topic I want to introduce is attention mechanism. So attention mechanism basically similar one human behavior. Is that humans usually focus on important things when they're doing every task. So for example, in the computer vision, some model will focus on the face of the dog to classify it as a dog, or it will focus on a part of the leg to recognize the dog. Apparently, the first option is better for the model to learn the pattern. And this also happens in traffic system. To predict the traffic conditions in one location, we can focus on the traffic conditions with low traffic density or high traffic density. And in the temporal dimension, to predict the future peak hour traffic, we can focus on the past peak hour traffic or the past normal traffic conditions. And we believe that by focusing on the important information, the model can achieve performance improvements. Attention mechanism also gain some confidence from the users. So as the users, when you train, because the model is trained using stochastic gradient descent, you probably will stuck in a very bad model. So of course, for a user, it is easy for you to pick the model based on the level of accuracy. But if two models, they have similar prediction accuracy, it's usually hard for you to choose. What we can do is, if the model is attention-based, we can extract what the model focus. And we can look at whether the model focus is similar to what human will focus. And if it is the same, humans are usually more trustworthy to that model with a similar focusing. Yes, so here is our proposed solution. Previously, I talked about attention mechanism. And attention mechanism is, so how exactly attention mechanism works is shown here. The leftmost model is the traditional attention mechanism. So assume we have the input, And for, I think we have 5 inputs. And for each input, we will calculate a query and a key. And based on the query and the key, we can calculate the attention score. So basically, the attention score represents the pairwise relationship between 2 inputs by taking the query of one input and the key of the other input into consideration. And then we will also use the linear mapping to calculate the value for the input. And here the final part is to have a simple matrix vector multiplication to get our final output. So in our proposed model, we are actually use 2 versions on the right. The key difference is that we don't apply the value mapping on our input, such that all the output of the attention layer will be just a linear combination of the input. So even though we stack many of these layers in our model, the whole model can still be explained using a linear theory. So which is the key difference. And so as I mentioned before, attention mechanism will capture some part of the information. But whether the part of the information is important, we don't know. So we will let the model to decide it by itself. As you can see, first we will have historical traffic data. And then in the horizontal line, we will stack multiple graph spatial attention layers. And in the vertical line, we will stack multiple temporal attention layers. So as you can see, we visualize the hidden what the hidden state represents in each output of the combination of graph spatial attention layer and temporal attention layer. As you can see, is that as we apply more graph spatial attention layer, so the hidden information will include a larger range of the node into the consideration. And if we apply more temporal attention layers, a larger horizon of the traffic data will be included in our hidden state. Doing this, we can capture the different capture the information with different combination of spatially and temporally. So this serves as a huge attention-based GNN model. And after we extract these features, we are going to aggregate all these features together for our final prediction, which is using another deep neural network. And we'll use mean square error to calculate the difference between the prediction and the ground truth, and use back propagation to train our model. So this is a case study. We use time space area dataset with 300 loop sensors collecting 4 months of data in a subnetwork of the California. The connectivity between the nodes is derived based on the real traffic network. And the input time length here is 7 days, not simply just 1 hour, history 1 hour. We are using 7-day traffic as the input, let the model to choose the important feature, and then use the important feature to predict future 12 hours. This is our basic experiment setup. So first, we observe is that our model can achieve 40% prediction accuracy improvement compared with most black box models. So in the figure, the x-axis is the time, and the y-axis is the speed. So the green line there, the green line there is the ground truth traffic speed. And the blue line there is our prediction. And the other line is just the prediction of other black box model baseline. So of course, we observe that it is not the perfect prediction, but actually predicting what happened in future 12 hours is pretty difficult because traffic is more like a stochastic system. So, but at least the model achieves much better performance than other baselines. So next slide is to explain what the model achieves and what the model focus for the cherry prediction. So first here, this is spatial attention distribution for the Monday cherry prediction. and we extract the two most important feature maps. That means that the model will highly focus on the historical data of the predicted node itself, and also relying on a very specific node that's far away from it. And we extract the temporal attention of these two nodes for the prediction. So as you can see in this figure, for this figure, first we observe is that our model can actually capture the weekly and daily periodical pattern of the traffic system. As you can see, for prediction, for Monday traffic prediction, the model will focus on every weekday traffic for its final prediction. And what we can observe is that the model will not focus on any traffic conditions of the weekend traffic, which also makes sense because weekend traffic and weekday traffic usually are different. And the other thing is that because our predicted horizon is 12 hours, so what we observe is that the model will only focus on the first 12 hours of every day of every weekday, which is not focusing on the whole day traffic data. And here, this vision map, I think most of us will be like confused why the model will focus on some location that is far away from its predicted location here. But what we find is that because actually the traffic pattern of this node is highly correlated with the traffic pattern of our predicted node. And because the model is focusing on 12 hours traffic, usually it will capture some recurrent pattern. So it's not like I will capture what happened simply in previous 1 hour, but capture more recurrent pattern. So, and the model feel like that this location have a very similar pattern. So the model will highly focus on this location for the prediction of the target node here. What we want to show here is another experiment that we use our model for a relative short-term prediction. So here we change the prediction horizon to be 1 hour. And this is the prediction horizon 9 to 10 a.m. on Tuesday. We also observe that the traffic pattern of the node itself is important because the node usually will repeat what it happened last week. And we also observe a very interesting spatial attention distribution in our second feature map. So it is very strange because the predict node is here. So based on the intuitive, which only focus on the node location around the predicted node. However, our model focused on here. And one explanation is that we find the residence density of the samples. Because it is 9 to 10 a.m. on Tuesday, so people will leaving their home for other places, which means that usually the congestion will appear when the residence density is high, especially in the location where two highways are connected. This is kind of explain why my model will focus on this location to predict the Tuesday peak hours. So this is our conclusion. We kind of explore and explainable machine learning models that can outperform most black box models in the task for long-term traffic forecasting. And the prediction can be interpreted using the attention mechanism. Our future is like whether it's possible to let the model learn more complicated, that we don't know any pattern systems. Yeah, with that, I'll conclude all of my presentations and thank you for your time and please feel free to ask if you have any questions. Thank you.
I think now we'll open for questions. I don't see any in the chat, but we'll start with the room. Are there any questions for us?
A couple of quick ones. Why did you pick data from San Francisco? Why did you come?
Why did I take data from San Francisco? Yeah, so when we take data, we have multiple choice like the urban traffic data or the highway traffic data. But urban traffic is usually controlled by the traffic signal, which is highly relying on how we manage the city. Because for that part, for the traffic policy part, we don't have too much exact information. So we start with exploring the dynamic of the highway system. And for the highway system, there's a very strong data set in California, it's Tennessee, so we choose that.
And in this slide, actually, it was interesting to know the speed. No,
sorry, this slide?
Is this speed the aggregate of the whole network or from a node
Oh, for specific node.
for a specific node? And how about, have you tried to see if it predicts overall
Oh, right, yes.
data?
Yeah, we actually have the results for predicting a whole node, but we don't visualize that. Usually the mean absolute error is 2.6 for a model, and it's like 6 to 7 for other data. Yes.
You mentioned you use spatial-temporal patterns. So you got the spatial pattern from graph neural network, right?
Yes.
So how do you embed these spatial patterns by using your graph neural network? Embed the spatial patterns.
Do you mean how do I embed my spatial-temporal pattern inside the model? Yeah. So the intuitive idea of the model is, for a huge amount of input data, we don't know where is the importance data. So we will have different combination of the spatial aggregation and temporal aggregation, and simply let the model to choose what is the important pattern, and then the model will use this pattern to perform its final prediction. And the idea is that the model is not human. It cannot extract the important pattern based on its intuition. But in order to push the prediction accuracy, the model will extract more important information for itself. Hence, we can know what important traffic features that the system has, which is the traffic pattern that we learned from the model.
So you predict the speed from different graph, or just get the speed from a static node for your graph neural network.
Sorry.
I mean, how do you get the speed?
Get the speed data.
Yeah, because you have to predict the speed from the graph neural network. So it could be node classification or graph classification for your graph neural network. So I don't know how do you get the speed from your graph neural network.
So I think, yeah. So maybe I didn't explain this part very clearly. Yeah, sorry. So basically the speed is our input data. So which is shown in here. Yeah, this part. This is where my speed is.
So it's time series data, right?
Yeah, it's time series data. And the thing that my model do is to tell you which part of the speed data you should use for your final prediction.
Have you ever tried some time series model like LSTM or other models?
Yes, LSTM is actually more weekly baselines, which, yeah, I didn't show it, but like Autoformer is I think it's the baseline, the best baseline in the transformer state of art, which is outperform LSTM.
Time series data, why would you want to use graph neural network?
Yeah, so because it's not a simply time series data, it's correlated spatially, right, in a network. So using the graph structure into the input will help to improve the prediction.
idea about it, so you mean like the check is a lot of stochastic like information, so you can get into the perfect predict the result. Did you at some point in during the training, so the noise is like in the mean of standard deviation, information of the input picture, and then you like randomly input the noise and let the network they encounter some like accident.
Yeah. Thank you for the question. And actually, this picture may partially answer your question. Hopefully, is that I think adding noises and is like you add some uncertainty into the data, and also like many deep learning model, such as deep ensemble, it can take basically I train 100 neural networks, and I let every time I let 100 neural networks to help me do the prediction, which is similar to the idea that you can quantify the certainty of the prediction. But doing this thing may be time consuming, and and I agree that it's one way to make your prediction more reliable. But attention mechanism, I simply use one model that would usually build more confidence for the users, because the user can more intuitively to see, oh, the model is looking the same thing as me, so I would more willing to trust that. That's the idea of the research.
Yeah. Regarding your initially construct the graph, so does it mean that for each point you have the spatial data and the time data? So you connect to the next node by like using kind of like the neighbor of the neighbor node in the spatial, the neighbor node in the time, and then together all you are with.
So the input will be the time series of each location and only the adjacent image of the network. So
so you only connect the constructed node by the spatial distance, not by the time distance.
Constructed node.
Yeah, the node in the graph.
The node in the graph is
How do you determine this node to be connected to the node?
Oh yeah, so first is based on distance. Second is to check whether in reality there's like a link between them.
I have a question from the chat from Evan. What do you suggest the user can do quickly determine if the model is paying attention to the wrong features? And what are the countermeasures to avoid this happening?
Yeah, so if the model is paying attention to the wrong features, but it can get good prediction, that will be another research topic, right? Maybe machine learning something more than one dimensional. But otherwise, the better way is to retrain that using so retrain the model again, and hopefully you can get more explainable model. That's the right. If we got the model focusing on wrong things.
And then another from Jesus, provided that this model is trained on historical data for a given geometric setting, could this model predict traffic conditions for hypothetical changes in the future? Examples are linear expansions, reduction or changes in signal coordination.
So yeah, so I'm not too familiar with what Hassis mentioned, but basically the model can take care of, like, theoretically can take care of any spatial-temporal correlated dynamic. Could you repeat the question? Or?
So I think what he means is, so it's based on historical data. If there's a change in the physical nature of the system, say the coordination of the signal has changed, there's an additional link, so the capacity. So then how does your model now function if it was trained in historical data?
Yeah, actually, that is related to another research area, dynamic graph. So for my model, we cannot do that. In the future, the adjacent image change. Maybe a dynamical graph can help for this.
very additional question.
I have like one, just simple question since you have this plot here. In using this protocol, how will this be integrated when there are autonomous vehicles on the road?
Yeah, so when autonomous vehicle, so the why I want to show here is because in autonomous vehicle, you may need to route them, and you have better send it to the traffic, the lane with low traffic density. So if you probably send a wrong vehicle to a high traffic density and come to an accident, then probably will lead to some critical consequences. Hence, we want our cherry prediction model to be trustworthy and reliable. Is what I want to show. But there's actually some research, like consider the connected vehicle as a dynamical graph and predict the behavior of the connected vehicle.
Thank you. Let's see any more questions in the chat.
I had another question. I was curious about the real-time location. Is it possible, or is it time consuming?
So
Yeah,
you might repeat the question because we have people.
Yeah, I was wondering about the real-time application for the model.
Yeah,
It's
it's a great question. So, basically, use this model for inference, not for the training. For inference is 1 second for predicting the future 1 hour or 3 to 4 hours. So I think it will be applicable in real time.
It's a random question. So in Google Maps, you can ask, right? When you're traveling, how does that differ from what you have done?
In Google Map,
You can ask, say, I'm gonna travel tomorrow at this time, and then it has a prediction. I was just curious, what is the difference in their implementation versus what we presented for today?
yeah, so for long term, because in research paper, there's not many people working on long term, but of course some travel business they already may have their own model. But whether the model is reliable, that is another question. And so one difference, if they can do long term, then maybe we can do the same thing. But one extra difference is that our model can provide more explanation for the users, which can make them more trustworthy.